For our project and final lab, we built an 8-bit CPU. And before we get into the actual circuit and the simulation, and just to give a bit of context for the design, I'll quickly go over the instruction set we used. So our assembly code follows the general structure seen here of a mnemonic command followed by the operands and then the destinations. And our instruction set contains about 65 different opcodes. Our instructions are all 16 bits wide and follow one of these 4 formats, which you can take a closer look at if you want. And here is an example of a small program that will just loop infinitely, and then what it will assemble to. And then we'll show this program running in our CPU a bit later in the video. This is our main circuit of our CPU. We use a word size of 8 bits. So our memory down here is 8 bits wide, and we have 256 addresses. All our general registers are also all 8 bits, and we have 8 of those. Then we have some special registers up in the left-hand corner. We have the instruction register that stores the current instruction, program counter, accumulator, a secondary just B register, and then our flags register. Right below that, we have some bus control. It's basically just controls inputs to various components like the general registers and the memory and the special registers. And then over on the right, we have our code memory where we store instructions to be executed. And our instructions are all 16 bits wide. And then we have the ALU and the control unit and our clock down in the right-hand corner.
Yep. And it's worth noting this is probably this is not a von Neumann architecture. The size of the code and data are separated into 2 different regions of memory, and they're not even the same size of words. So it's a little messy, but it works. So briefly go over the ALU. I think at this point, anyone looking at a project as complex is probably familiar with the basics of building an ALU at this point. It just does arithmetic and logic. This one just does a few operations like addition, subtraction, multiplication, signed multiplication, division, and signed division, basic logic operations and shifts. Takes 2 inputs, X and Y, and an opcode to select between the results and the current flags register. We've only used the the high 4 bits of the flags register, so we just pass on the first 4 bits as if nothing changed. And then there's actually 2 outputs. Most operations will only use 1, but some of them, specifically the multiplication and division, use 2. That's because multiplication requires twice as many bits to store the output. So the high bit of multiplication is stored in the B result, which later gets stored in the B register. And for division, there's also a remainder that is stored in the B register. So that is the entirety of the ALU. For the control unit, we kind of cheated our way through this. This is interesting. So the control unit stores and maintains the current phase of the machine instruction cycle. Due to the initial design of this, we only actually ended up using the first 2 phases. Everything fit in there, which is pretty cool. I probably could have reduced that to just a 2-bit counter here. We could have used Logisim's built-in counter, but that took up way too much space in the screen, and I didn't like that, so we're using a register and counting ourselves. It also takes in the current clock value and the current instruction, which is stored in the instruction register here. The control unit can specify using this right here, that output, whether or not to actually write to the instruction register. And it also takes in the current flags. So all these outputs over here are used to determine what memory is actually moved around to where. So those will come out right here from the control unit and determine which of these are sending data to which parts of the CPU. Within here, yeah, again, we cheated our way out of this. This programmable map stores 32-bit words. There's 256 of them, one for each possible opcode. We've only utilized like, I think 60 something of the actual opcodes you could have out of 256. So, and that's kind of efficient, but also we still have a lot left to use. So the way this works is we were really lazy. And we specified this in an Excel file, which I know is like gross, but so this specifies everything we need. At the top here, we specify the amount of data each one of these things is going to take up in this row. There's the bit width of those data items, and then each one of these columns stores information such as the corresponding ALU operation for the instruction, which data item to select for the inputs for a operation to the ALU, and other things. Usually things that end in an S select the data item that will go into some kind of register, and things with an E on the ends are for determining something more like whether or not you're allowed to actually write to that register. So we have quite a few things in here. I'll go over an example in a little bit. This then gets compiled by Python code, which I don't have up right now. Assembler, very large assembler, which was, we have two versions, one of which Ethan wrote, which is pretty nice and got us testing much faster than this one did. This one's a little bit cleaner, but they both work pretty well. So we take that and we can load that into here by just right-clicking on this, hitting Edit Contents, Open, and then we just take our map, which is located somewhere in my computer if I can actually find it. CU programmable map, and we can just open that up and it will load into Logisim. And so that gets each word, which depends on the current opcode, which is the first byte of the instruction, is used as an address into the programmable map, which is then split up into all these different outputs that are then sent out. The immediate value, which is also part of the instruction, is also split off here, as well as any register indexes if there are any for an instruction. And though they're also sent out as outputs. So right now we have a simple program loaded into here, which is an infinite loop. Here's an example. This just moves data items around. We're not using the ALU here. This simply begins by moving the preparing the upper byte of the PC by moving 0 into the accumulator, then moving the accumulator into the 0 register, and then it also moves 0 into the accumulator register, which effectively sets up an address of 0, which is the beginning of the file here. And then we proceed to jump to that address here, which jumps us back to the very beginning. So I will just run this program. It is already loaded in here. You can see the instructions here coded in hex. They only each take up 4 digits in hex here. So simulate. We're running at 16 Hertz. Enable ticks. And there you go. You can see it running. And each time it just jumps right back to the first part again. It is worth noting you'll see it temporarily flash down to here, and the reason for that happening is that every time we get to the fetch instruction, it automatically increments the counter to the next point in memory first, and then when we get to the actual decoding phase or whatever comes next, it is then moving us back to something else. But that's why it temporarily jumps down there.